Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 4, Lesson 4, Linear Inequalities in Two Variables. After this lesson, you'll be able to graph solutions to linear inequalities in two variables. And we've got some new vocabulary. What is a linear inequality and what is the solution to a linear inequality? It's very similar to a linear equation. We just have a greater than or less than symbol. For the model and discuss, we have this situation. A flatbed trailer carrying a load can have a maximum total height of 13 feet 6 inches. So 13 feet 6 inches, if we do 13 times 12 plus 6, we get 162 inches. That's the maximum height. The photograph shows the height of the trailer before a load is placed on top. So the height of the trailer is 5 feet, which is 60 inches. Okay, so that means a load, the difference, then, can be 102 inches, right? If the total distance can't be more than 162 inches. So the maximum that a load, something can go on the trailer, can be at most 102 inches. What type of model or equation could represent the situation? Well, since we have a maximum height, and we could have anything shorter than that as well, we could use an inequality. So, in a sense, anything less than or equal to 102 inches would represent the height of the load. Will the type of model, or this equation, show all the possible heights? Well, yes. Anything less than or equal to 102. So 100 inches, 98 inches, 72 inches. Anything and everything in between, even decimals. It includes all of the possible heights, less than or equal to 102 inches. And so that's what the solution would be. Okay, so the load can be less than or equal to 102 inches or no more than 102 inches. And we can use an inequality to represent that situation. So how can we use a graph to show the solutions for an inequality with two variables? So in two variables just means we have x and y. And you can see, here's our first inequality. It's linear because it looks like slope-intercept form. It looks like y equals mx plus b, doesn't it? It just has a different symbol. Instead of an equality sign, we have an inequality sign. But we're going to treat it like a linear equation. The solutions then would be all of the values for x and y that would make this inequality true. So all of the possible points, x comma y, that would still make this linear inequality true. So if we were to plot this equation as if it were y equals mx plus b, the slope then is 1, okay, because the coefficient in front of the x is 1. The y-intercept is -1, and we can graph that. So we plot our point at -1. And we do our slope of up 1 over 1, up 1 over 1, up 1 over 1. And since it is equal to x minus 1, we're going to use a solid line. The solid line says that the values on the line, or equal to x minus 1, are solutions. So we're going to make this a solid line because it says equal to and less than. How do we show the less than part of our inequality? Well, pick a value that would be less than x minus 1. So here, this value, when x is 3, my y value is 2. That is less than 3, right? My y value of 2 is less than or equal to x minus 1. What if I did this point right here? X is still 3, but now my y value is at 1. 1 is still less than. So if I plugged in that value of y, okay, so I'm going to write this out. We're going to look at this point right here, 3, 1. 3, 1, 1 is my y variable. 1 is less than or equal to 3 minus 1. Is this a true statement? Yes, 1 is less than or equal to 2. So that point would work. What about this point down here? X is 3 and y is -2. So let's plug that into our equation. -2 is my y value. Will this make the equation true? 3 minus 1. Yes, negative 2 is less than or equal to 2, positive 2, so that is also a solution. So since all of these points on this blue ray would also make the inequality true, they are also solutions. So that's why we will shade below that solid line. You can see that here. So we shade everything below that line to show that all of those points, all of those ordered pairs would also be solutions to this inequality. Any point in that shaded area would be a solution or would make that inequality true, as well as a point exactly on the line, because it can equal x minus 1 also. What if we have an inequality that does not have an equal to? So here we have, now it's greater than, but not equal to. So we're going to graph that line again, the same slope. Slope is still 1. Y-intercept is still negative 1, so we still have that same line, but now you see it's dotted. We do not fill a solid line because it is not equal to that value. It's just greater than. So when you do not have an equal to, it's going to be a dotted line because it's not equal to that linear equation. Now, how do we find the other solutions? Well, again, you can just pick a point. So let's pick 0, 0. And let's plug that into our inequality. 0 is my y value, greater than 0 minus 1. Is 0 greater than negative 1? Yes, it is. So that is a solution. Pick another point just to check. Let's do 0, 2. Okay, 0, 2. So my y value is 2. Is that greater than 0 minus 1? Yes, 2 is greater than negative 1, so that is also a solution. So since these points above the line are solutions, we're going to shade above the line. So a way you can remember is if it's greater than, it's above the line, and if it's less than, it's below the line. Try it number 1. Describe the graph of the solutions of each inequality. Let's describe it, and then let's go ahead and try graphing it also. So you can see they're written in slope-intercept form. Let's identify the slope. The slope for the first one is negative 3. The y-intercept is positive 5. So we can graph that. 2, 3, 4, 5. And the slope is up 3. 1, 2, 3 over 1. And reverse it and go down 3, left 1. So here is my line. I'll do one more point. 1, 2, 3 over 1. Okay, now, before I draw a line, I'm going to think, is it going to be a dotted line or a solid line? Well, there's no equal to, so it has to be a dotted line. So then you can use your straight edge and do a dotted line as you connect those points. So just make sure you do a dotted line as you connect with the straight edge. And still put arrows on the end. Okay, now we need to figure out which area do we shade? Where are the other solutions? Since it's an inequality, we have to show, is it above or below the line? This is less than, so I'm thinking less than is below. Let's shade below, and let's just check. Let's double check by picking a point. Well, 0, 0 is below. Let's plug this point in and see if it is a solution. Okay, so 0 less than negative 3 times 0 plus 5. 0 is less than 0 plus 5. Yes, 0 is less than positive 5. That is a solution. So everything below the line will be a solution to that inequality. Okay, let's do the next one. Identify the slope. Again, it's negative 3. The y-intercept is positive 5. So we're going to have the same line. Okay, 1, 2, 3 over 1, 1, 2, 3 over 1. Okay, there's our line. Now, before I draw my line, before I connect my dots, let's check our inequality symbol. It's greater than or equal to. Since it's equal to, I know that this line could also be a solution. So a point on the line could work. So we're going to make a solid line through those points. And then since it's greater than, we're going to shade above the line. And no, it technically looks like it's to the left, but if I were to balance out that line by pushing up on that end, then the green part would be above. Let's choose a point to verify that we shaded the correct area. So what if we chose something on the y-axis? Let's choose this point here. It's in my shaded area. 0, positive 7. Let's plug that in to our inequality and see if it works. 7 is greater than or equal to negative 3 times 0 plus 5. 7 is greater than 0 plus 5. Yes, 7 is greater than or equal to 5. So that point is a solution. So then we would shade everything above the line. Application problem. The Science Club sells t-shirts and keychains to raise money. How many t-shirts and keychains could they sell to meet or exceed their goals? So this is key information. They want to meet, so exactly or greater than. We're looking at greater than or equal to a value if we're meeting or exceeding. And you can see in this graphic, their goal is to raise $750. So this was a typo in the text. It should say $750, not $500. And we can see t-shirts are $15 each and keychains are $5 each. We're going to say X is the number of t-shirts and Y represents the number of keychains sold. So then to write our inequality statement, 15X, because that's the cost of the t-shirts, plus 5Y would be the total cost of the keychains at $5 each, is going to be greater than or equal to $750, which is their goal. So there's our inequality statement, and we can graph this by looking at the x and y intercepts. Since it's in standard form, we're going to graph the x and y intercepts. So remember, that's when y equals 0, x comma 0, and when y equals 0. So when x equals 0 and when y equals 0 are our intercepts. So if we plug in 0 for y, like we did here, we get x equals 50. So there's our x-intercept. And if we plug in 0 for x, we get y equals 150. There's our y-intercept. And then we can graph those 2 points. Here you can see they've graphed those 2 points. Here's 150. Here's x equals 50. And since it's greater than or equal to, remember our equation had greater than or equal to, we can have a solid line. And it's greater than, so we're going to shade everything above the line. To do a test point, let's pick a point like 60, 40. And if we plug that into our equation, 15 times 60 plus 5 times 40, is that greater than 750? Yes, 800 is greater than or equal to 750. So we did shade in the correct place. So for the try it, how would selling 40 t-shirts and 95 keychains result? Would they meet their goal? So this is just 40, 95. That's our point. Remember, x was the t-shirts and y was the keychain. So our point, I copied the graph that we already have. So at 40, 95, somewhere around here, is that in our solution area? Yes, it's in the shaded portion. So that would meet their goal. We could even solve it algebraically if we wanted to. 15 times 40 plus 5 times 95. Is that greater than or equal to 750? 600 plus 475. Is that greater than or equal to 750? Yes, it is. It's 1,075. So that is definitely greater than. They did exceed their goal. Example 3. Now we're going to work backwards. We're going to be given a graph and we need to write the inequality statement or write the equation. Okay, so let's just take a look. What do we see? Well, I see we are shaded above the line, so I know I'm going to have a greater than. And I see that it's a solid line, so I know there's an equal to. Now we need to find the equation for the slope and the y-intercept. So let's identify the slope and the y-intercept of this line. The y-intercept is at -3. And from there, looks like we go up 1 over 1, up 1 over 1. So our slope is +1. So then our inequality statement, it's going to look like slope-intercept form. Y greater than or equal to m is 1, x plus b. And we don't have to write the 1. It's an invisible 1. So our inequality then is just y is greater than or equal to x minus 3. So make sure you identify if it's greater than or less than, and then look at the line to see if it's solid or dotted to determine if it's going to be an equal to or not. So what inequality does each of these graphs represent? Okay, so let's first look at the shaded area. It is below the line, so I know this is a less than. It's dotted, so there's not going to be an equal to. So now let's identify the y-intercept. The y-intercept is 0, so it's going to be a plus 0. What's the slope? Looks like I go up 1 over 3, so the slope is 1/3. So then we just plug that into our slope-intercept form. Y equals 1/3 x plus 0. I don't have to write the plus 0. Okay, for the next one, same thing. We shaded, now this is tricky. We shaded to the left, but look, we have a downward slope. So if I were to push this line up and even out that line, make it horizontal, I would be shading below. Okay, so this is shading below the line. Notice I know it's to the left, but we have a negative slope here. So it's technically to the left or below the line. So this would be a less than symbol. It is a solid line, so we know it's also equal to. Now we need to identify the slope and the y-intercept. The y-intercept is at positive 1, and the slope is negative. We go down 2 over 1. So negative 2 over 1 is our slope. Put that into our slope-intercept form. Y less than or equal to negative 2x plus 1. Example 4, inequalities in one variable in the coordinate plane. So we've seen these special type of equations before when we were doing linear equations. So now there's only one variable. There's no y variable. Y really is just 0. Okay, so what this says is x is always greater than or equal to 3. That's what that says. Can we graph that on a horizontal number line? Yes, we can. We can graph that on a horizontal number line. Since it's equal to, we have a solid circle at 3. Greater than is everything to the right. So here is our horizontal number line graph. And we could think of this being the boundary. Okay, right here is the boundary at 3. So at 3, it's a solid line because it can equal 3. And then everything to the right would also be a solution. Okay, so everything to the right would also be a solution. So you can just graph it like you would normally graph x equals 3. Graph that line. Then you would need to look and say, is it going to be a solid line or a dotted line? Since it's less or greater than or equal to, it is a solid line. So we graphed that line at x equals 3. And then we just determine, is it to the right or to the left? Is it above or below? It's greater than, so it's going to be to the right. Or when x is greater than. Remember, greater than goes to the right. Okay, so here's our other special case equation. We do not have an x variable now. So again, this says y is always less than 2. Y is always less than 2. So no matter what, y will be less than 2. If we graph that on a vertical number line, we see here we have an open circle at 2, and everything less than is going down. I'm using a vertical number line now because I'm dealing with a y variable, and y variables go vertically. Okay, so here's our boundary now. Here's our boundary at 2, and since we have an open circle at 2, we have to have an open line or a dotted line, right? It's not a solid or filled in line. So dotted line at 2, because it cannot equal 2, but everything less than would be below that line. Try it number 4. Let's graph these special case inequalities. So again, we're going to just draw our graph at y equals negative 2 first. And I know it's going to be an open line or a dotted line because it does not have an equal to. So first let's draw that line. Y always is at negative 2, so all the points would be at negative 2. No matter what x is, y is going to be at negative 2. And since it's greater than, but not equal to, these are going to be a dotted line, so not solid line at negative 2. Greater than is everything above that line, so then we would shade above. Don't forget to shade, and don't forget to check if your line is solid or dotted when you're doing inequalities. Okay, let's do the next one. X is less than or equal to 1, so we can just think of graphing x equals 1. It is equal to, so we can do a solid line where x is at 1. So x is 1 no matter what y is, x will equal 1. It's going to be a solid line because we have the equal to. And then if it's less than is going to be to the left. And we would shade to the left of the line. That's it for lesson 4, linear inequalities in two variables. So the things you need to watch out for, check the symbol. If it's an equal to, it's a solid line. If it's not equal to, it's a dotted line or an open line, just like with horizontal number lines when we graph inequalities. And then you need to shade either above the line for greater than or below the line for less than. If you have any questions, put them in the comments and come back for lesson 5.